We discussed the first isomorphism theorem for groups. It says that an image is a natural quotient. Suppose that we have a homomorphism F, which goes from a group G to a group G tilde. So it preserves the group multiplication. Then we can ask, is the image of F, which we call H tilde, is indeed a natural quotient? And the theorem says that we have an isomorphism, F tilde, which goes from G over the kernel of F, which we will call K, to H tilde, the image of F. This is an isomorphism, and it maps a coset GK to F of G. So, and this is an isomorphism. This is the first isomorphism theorem for groups. So let's prove it. First of all, of course, the kernel of F, which is K, needs to be a normal subgroup in order for us to be able to quotient by it. Well, is it? Well, suppose we have an element K of K. Then the question is, does GK, G minus 1, is that also mapped to the identity in G tilde? The answer is yes, because we can put F inside the bracket. F of K is then E tilde, so we just have F with F G minus 1. These are each other's inverses, so indeed we get E tilde, and K is a normal subgroup. Similarly, it's easy to prove that H tilde is indeed a subgroup, not necessarily normal. Now we have to check whether F tilde is well defined. This we do by supposing that we have GK equal to G prime K as cosets. Then this immediately implies that G is G prime times an element in K, and therefore F of G is F of G prime K, which is by the homomorphism property and the fact that F of K is the identity, this is F G prime. So indeed, the map is well defined. So then thirdly, is F tilde a homomorphism? That's easily established. F tilde is a homomorphism. Then is F tilde injective? Well, let's suppose that F tilde of GK is equal to the identity. Can we then prove that F tilde GK has to be K, namely the identity in the subgroup, in the quotient? Well, we have that F tilde of GK is equal to F of G. So if F of G is equal to E tilde, well, then G is an element of the kernel, and therefore GK is nothing but K, which is the identity element. So indeed, F tilde is injective. Now, is F tilde surjective? Surely, because any G can be chosen in GK, and therefore any F of G is reached by the map F tilde. So we have a homomorphism, which is injective and surjective, and therefore F tilde is indeed an isomorphism. So we have an isomorphism from G over the kernel of F to the image of F if F is a homomorphism of groups. So this is often applied when F is an epimorphism in which case the second member is just the target group.